I'd like to introduce our next speaker is Stacy Weinstein-Weiss from JPL, who I've had the pleasure of working with for, I don't know, about a year now, I guess, on interstellar precursor studies. There are several that are going on, and she's going to give a snapshot not of a precursor, but of the latest thinking on a full-blown mission to an exoplanet. So I'll turn it over to Dr. Weinstein-Weiss.
Thank you. Hi, everyone. So I work at the Jet Propulsion Laboratory. I've been there 30 years now. I'm currently the Deputy Payload Manager on the Europa Clipper mission, which will launch in 2022 and go to do a number of flybys of Europa, looking for habitability or signs of habitability. First of all, I want to give credit to the team here. A lot of us worked on this paper, and two of the authors are right here in the room. One of them is Les Johnson, and the other one is Slava Turishev, right back there. But there were a lot of people from a lot of different centers and institutions, and even a couple of retirees came and joined the crowd, so it was a lot of fun. Next slide, please. We've been really successful. We found 3,500 exoplanets now with thousands more to be discovered, and that begs the question, and people have been asking it at open houses, when are we going to send a spacecraft there? Well, gee. So we said, okay, let's take a look at it. Our study team kicked off in April 2017, and we wanted to develop a mission concept and technology requirements for the first scientific robotic exploration mission to an exoplanet. So why is the mission concept important? Well, if we don't start with a mission concept, we might forget to drive requirements on key technologies. So we want to see the whole picture, not just solve one aspect of the problem at a time. And why a science-driven mission? We'll talk more about this later, but in the end, it best answered the question, what makes a mission to an exoplanet compelling? In order to get NASA to fund it. We don't have billionaires necessarily that could bankroll it, so we have to work for NASA and the taxpayers. So what would make them direct the billions of dollars that they get away from other things and to a mission like this? The other thing we considered was making this mission architecture extensible to the future. In other words, some people had really neat ideas for how to get to an exoplanet, but it would only work if it were a trinary system. Well, we don't want to necessarily limit ourselves just to trinary systems, so we want to develop an architecture that can go to a number of different exoplanets. Now, this doesn't argue against precursor missions, and we'll talk more about that later as well. I think there's a lot of value, and in fact, it's necessary to do precursor missions of different types. So our charge to the team was think out of the box, be creative, have fun, but back your ideas up with sound physics. We ran in think tech mode because we really had no funding. So we'd meet every week or every other week for about an hour and discuss different topics, propulsion, power, navigation, communications, that kind of thing. We took a look at different mission design techniques. Do we do a fast flyby? Do we brake at the target? We talked about, is it okay to just slow down but still fly by? We looked at all kinds of different propulsion, nuclear, electric, beamed energy, fission, beam power, fusion pulse, the Bussard ramjet, antimatter. We talked to Les about the e-sail. We looked at optical comm and microwave. Of course, we talked about radio for communications as well. Oh, sorry. And then for power, we looked at radioisotope, kind of like what we've been using today for Voyager and Cassini, fission, beamed, and antimatter. And I'll touch more on those later, but let me just address antimatter right now. While we all look at what it could theoretically do and go, wow, that'd be really great to have. In order to, we don't make a lot of it today. It would take a long time to make a lot of it. And even if we could make a lot of it, and even if we could contain it successfully, one cosmic ray could kill the mission. And that's just really hard to protect from. So we crossed that off our list. Sorry about that, but it's a goner. So we started writing down our mission requirements, and we did this iteratively. We started with a few, and then we altered them as we went along. So, for instance, the flight time to the target should be less than 50 years, pending confirmation of a suitable target. And that's because, again, we work for NASA, and the mission has to be politically and humanly palatable. folks don't like to think about missions that are long duration. Even trying to get our mission to Pluto, New Horizons, going, it took well over a decade just to get it solidly on the books, because it kind of did nothing scientifically for a decade and then flew by the target. And that was a hard sell. That was a very hard sell. There should be meaningful science return at least every decade en route to the exoplanet. So this is one way of getting around you guys are going to spend 50 years getting there and do nothing on the way. Well, there is valuable science we can do on the way, and we can talk about that in a couple of slides. The primary objective of the mission shall be to confirm and characterize life at the exoplanet. Now that one actually wasn't one of our original objectives, and this is something that we derived, and we will talk about that more. But it also turns out that NASA's strategic objective is to discover how the universe works, explore how it began, how it evolved, and search for life on planets around other stars. So there it is. That doesn't mean that every mission has to do that. Obviously, none of them are right now, but it is one of the NASA goals. So the threshold data shall arrive at Earth in less than 70 years from launch, and that's because we want the data to come back within the professional lifetime of someone born around launch, and that way they can be inspired by the mission and work on the data when it comes back. It's just basically a way of setting an end bound, because we could talk about missions that take 200 years. The first bit of exoplanet science should arrive at the Earth 5 to 10 years after exoplanet arrival. However, then we started looking for exoplanets near Earth, and there wasn't much within 5 to 10 light years, and so we actually said the exoplanet target shall be within 15 light years of Earth. So we probably need to go back and revise number 5 there, although to be fair, we don't have to wait until we actually get to the exoplanet to start returning science data from it. With a good camera en route, you can be back a ways, but five light years is sort of a stretch. So the idea there is if we're going at a fraction of the speed of light, 0.1, 0.2, then the exoplanet target should be within 15 light years of Earth. That gets you a 50-year travel time and 10 to 20 years to collect and send back data. And let's see, per the 100th anniversary of Apollo, the launch date shall be no later than July 15th, 2069. Where'd that come from? Well, Representative Culbertson, who's the champion of the interstellar mission, proposed that date. So we said, oh, it's as good as anything. Other assumptions, and these are kind of key now. So the exoplanet target shall have been previously observed and resolved to 1,000 by 1,000 pixels or to 1 pixel with promising biosignature lines. And this is so that we have an idea of what kind of instrumentation to bring and what kind of performance specs they should have. For instance, it would be really a bad day if all we had with us was a really good camera and we got to the exoplanet and it was covered in clouds like Venus. Ah, darn. So we want to do some characterization up front. We'll have TBD accuracy on the ephemeris. We're still talking about what we need, but actually what we have today is sufficient to do navigation, and that's because we already have the autonomous onboard navigation capability. We demonstrated it on Deep Impact. We'll talk more about that in a bit, but we will get better accuracy on the ephemeris. And what I mean by that, for people that don't know, is the orbit, how precisely we know the orbit of the exoplanet that we're going to. We know that fairly well for most of them today, and with the big telescopes that are coming online in the future, we'll really nail it for our purposes. And so we're not constrained to today's technology, but there should be a reasonable physics-based path toward the near technology. So we could fly 3D printers and maybe rebuild parts of the spacecraft, maybe refresh our power converters, that kind of thing. But we should try and stay away from "and a miracle occurs." Okay, so key finding in response to an early driving question. What makes this mission compelling in terms of science return with respect to what we'll be able to do in a few decades with our near-Earth large telescopes, enormous space-based interferometers, which we kind of ruled that out after looking at it more. They just have to be too huge. The baselines would be astronomical. And or a mission to the solar gravity lens focus. The team determined that, much of what we've traditionally learned on reconnaissance missions will be gleaned from our future near-Earth telescopes or a mission to a solar gravity lens focus. So, we'll have the spectra. We'll be able to tell you about the atmospheres and the compositions. We'll know the size of the planets and the rotation. There's just a treasure trove that we'll get just by staying here. So what does that leave? Well, you can do magnetic field stuff, that kind of thing. But really the big one that would compel NASA to spend billions of dollars to go is to confirm and characterize life. Okay? And that was really a big, profound thing, and it drove the architecture. Biosignatures, as we know them today, cannot confirm life. You can detect a biosignature, and it can give you a smoking gun, but it can't confirm. So for instance, a recent paper, and I've got the citation there, and by the way, in our paper, we have lots of citations and references. So you won't see any equations in here. They're all in the reference papers, and you can go through them. Well, I feel bad because there were a lot of great equations in the last talk, and I have none, and so there you go. But anyway, okay, so the recent paper showed how Proxima Centauri Beta, it's in its star's habitable zone, and it could have an O2 atmosphere, but practically no possibility of life because of massive solar wind exposure. And so, there are things like that you have to weigh, and right now, the only way we know of confirming life is to land and sample. This could change in the future. Maybe within the next 50 years, we'll get so good at detecting life from afar that, again, we won't need to do this mission. But today, we would. So you got to land and sample, and that drives the mission to at least slow down and realistically break in orbit so you can send a lander down and get the data back. And that really is kind of a bummer because that severely limits our known propulsion options. And it makes the mission really, really hard. It makes it take twice as long. It doesn't preclude precursor flyby missions to explore the interstellar medium or validate key technologies. And in fact, those are encouraged and probably required if you start looking at it. So let's talk more about target selection. We'll come back to some of these other technologies. With over 3,000 candidates to select from and more in the future, the selection criteria for which exoplanet we go to is going to be hugely important. And these criteria will evolve. I'm going to show some on the next page that we thought up, but I'm sure they will change by the time a mission to an exoplanet is actually launched. But they'll evolve with our understanding of life and habitability. The exoplanet characterization required to meet the criteria, good news, is already in the astrophysics and astronomy roadmap. If you look at the JWST and the LUVOIRs and HABEX missions, if we follow that roadmap, we're going to get the characterization we need. So that's great. And again, a mission to a solar gravity lens focus is also desirable, if not required, for characterization because you get the picture, you get the images. So given our knowledge today, the following target selection criteria were suggested. So exoplanets that are in their sun's habitable zone, exoplanets with masses less than 2 Earth masses, those are rocky planets with a decent chance for an atmosphere. Exoplanets that experience roughly the same solar radiation as Earth, detection of the biosignature, we talked about that already. The current age and expected lifetime of the star should be such that life should have had a chance to form. That's 4 to 5 billion years, give or take. And again, these criteria will change as people become more informed. And the exoplanet star should be close to a G2V, which is our stars. And again, I want to caveat each and every one of these. They will change as we know more, as we learn more. So science objectives, ultimately the objectives will be determined by some kind of a decadal survey and NASA working groups, but the 5 main categories of science objectives suggested were heliosphere boundaries for our own sun, the interstellar medium and other science that we can do en route like astrometry, the astrosphere of the target star, the solar system of a target exoplanet, and the target exoplanet itself. The first 3 categories I mentioned can be achieved with basically the same instrumentation that Voyager had, but tuned to looking at the interstellar medium. Voyager was never intended to, look at the interstellar medium, and they would have liked to have had different instrumentation, but they're stuck with what they launched with. We can change. Science objectives involving the solar system of the target star are numerous, and they're the basic, initial reconnaissance objectives that missions in our solar system have had. So, composition and mapping, spin rates, moons, rings, dust, on and on. The science objectives involving the target exoplanet may include many of the basic categories above, but also, an orbiting mission can resolve rivers and forests and mountains, really get the geography, the geomorphology, the balance. The key mission objective that we chose was to confirm and characterize life. And so now we need life detection experiments. And ideally, you want multiple, unambiguous, independent experiments, so we don't fall into the Viking trap and continuously argue, well, did we see it or did we not? We want to have multiple detections. And other landed instrumentation could be, cameras, meteorology station, you name it. So let's talk a little bit about the mission concept architecture highlights. We ended up with a 2-stage light sail for propulsion. And before anyone goes running out of here saying, oh, they agree, it's got to be a light sail, it wasn't quite like that. It was kind of more like, this is the least bad of many bad options for propulsion. Let's be frank. The propulsion is the hardest part of the problem. And, in our think tank mode, we weren't going to solve it. What we were able to do was rule out a lot of things. And there are advantages, there are disadvantages. With a 2-stage light sail, and for those that don't know what I'm talking about, you're taking a laser beam and you are shining it on the sail for decades to speed it up and then decades to slow it down. So unlike Starshot, which only needs a laser for minutes, and quite frankly, lasers go for seconds today, if that, we would need decades. Okay, so that's huge. That's a huge, leap. And so you lace the sail, and then when you get to a certain point close to the exoplanet, you separate. You use the one sail as a concentrator and shine the laser onto the second sail, and you slow it down. Okay, and so one keeps rocketing on, and the other one slows down and goes into orbit. It's the easiest propulsion technology development path in terms of solar sails. We're right there. Obviously, we have further to go, but in terms of that versus fission or that versus fusion, we thought that in the next 50 years, this would probably be the place where we could, make the most improvement. It's the only option that doesn't involve a lot of onboard power, and we'll talk about that in a bit too. And lasers at Earth can be improved over the mission lifetime. So, if they burn out, you can replace them, that kind of thing. So that's kind of nice. The big bad problem, there are many bad problems with this, but the big bad problem is the power needed for the laser. We're talking petawatts, with a P, petawatts. We don't make petawatts on Earth today. So that's why I said this is the least bad of many bad options, and it is a bad option, quite frankly. In our paper, we say that this certainly needs a lot more work, the propulsion area in general, and we hope that someone comes along with a great new idea. Maybe a patent clerk, but something like that, to take a look at known physics but in a different way and come up with a different application. We also used LaserCom. We designed a 2.5-meter onboard LaserCom system. We'd have 100-meter light buckets in space. Now, putting it in space solves some problems. You get around the atmosphere. Obviously, it creates problems because you got to get into space, and it's very, very large. But you get away from the atmosphere, you get away from weather, you get away from eclipses and, the Earth rotating and stuff like that. Once a year, you're going to have occultation when you go behind the Earth from respect to wherever you are. But that can be planned around. And so what that does is the onboard power drops to 3.5 kilowatts, and it drops. Starshot's talking about a little power. But when you look at what historically has been talked about, megawatts of power. And in fact, if we didn't have a large collector in space, we would be talking about megawatts of power on board the spacecraft. So this drops us down to 3.5 kilowatts electric, and that gets you 100 bits per second for downlink. And again, if you've got a lot of time, you can get data down that way and stream it continuously or nearly continuously. For power, I didn't have it on the chart here. We took a look at that, and with plutonium-238, which we've used on many missions, and probably a dynamic, you could use passive, but you might want to go to a dynamic converter, you can easily generate this. So that isn't really a problem. And then we'd use autonomous onboard navigation. We have to. You just can't joystick the spacecraft from the ground. You're too far away, especially at 15 light years. This was proven on Deep Impact, as I said, but there's a new wrinkle, and that's the onboard autonomous mission replanning capability. So just as a use case, one of many use cases, you show up at your exoplanet, you spend time mapping it, collecting all the scientific data, and now you have to decide where to land autonomously without help from the ground. You have to create your landing profile, verify that landing profile with the lander, probably with an aeroshell that you brought from Earth, guessing at the shape of the aeroshell. Maybe you have to actually machine that in flight, and tailor it a little bit if you guessed wrong. All that has to be done autonomously. And then you land, and then you collect the data, and you do your life detection experiments, and you process that data, and you send the results back. Because there's just no way, not thinking about bringing a sample back to Earth, or not, but you do the amount of data to do landing site selection, to do the the landing data profile, the scientific data you collect. It's just way too much to all send back. So you literally have to have a scientist in a box. Here you go. So this is really hard, but it's worth doing, and it's worth doing right. It's worth taking the time to think through an extensible architecture. Many intermediate steps along the way, many validations to do. This architecture, I'm sure, won't be the one that flies as we continue to evolve in our understanding of our technology. Better things are surely coming, and better ideas too. But this is a first. This is a first target, but it is a science-driven mission to an exoplanet, which would be a very valuable thing to do. That's it.
We have time for a few questions. If you're ready, just go line up and ask.
I would suggest you potentially consider having the fast flyby be like a module on your craft, and then before you begin to decelerate it, you could simply release it, and it would be beaming back information from the flyby to the rest of your vehicle, which would then be better equipped to send that information back to Earth. So that would be one of your decade things, where you would be getting some information in advance as it fly by fast without ever trying to slow down.
Okay. No, just so I understand, you're talking about the same two-stage light sail concept, but just when we break them apart, have one be the precursor, or?
Well, the size you would need, if we're talking about anything like what the other group did earlier this morning, you would need almost no mass for this thing. If you were using this, in other words, it's little chip.
So bring a star shot like chip sail with it. Okay, I understand now.
But it could be big. It could be bigger.
Sure, absolutely. Thank you.
So I am the propulsion guy, and I was waiting eagerly for your talk for the bottom line answer, which is, what's the mass of the payload that you need?
Oh, what's the mass of the payload that we can bring with us?
Yeah, I mean, there's many propulsion systems, but it makes a big difference if you're talking about, a kilogram or a ton.
Oh yeah, no, we're not talking about the kilogram class. We're talking, more like a ton, although probably reasonably 500 kilos, something like that. Go ahead.
Have you considered developing any biomimetic type systems, sensory systems? In other words,
I'm sorry, say that again. Bio what?
Biomimetic type.
Biomagnetic?
Mimetic.
Mimetic. Okay, sorry.
Mimetic type
My hearing's
system.
bad. No, we have not.
Because it's, in other words, re-engineering an insect or something that you can release in many forms in the vicinity and then get information back from them.
Would the purpose of that be just so that you can have maneuverability move your instruments around,
Maneuverability.
sort of like a helicopter type thing. Or,
Right, so releasing a lot of small probes in the vicinity of the targets to,
We hadn't talked about that. No, we hadn't gotten past okay, you have to land and here's what you want to do. It could be a rover, it could be a series of landers, but again, in think tank mode, we didn't get the luxury of spending a lot of time on any one section. Okay.
Any other questions?
Oh, one more.
About the power supply problem,
Uh-huh.
if you're moving, did you give a speed? If it's like 0.1 C or something?
Oh, yeah, we'd need to be between 0.1, 0.2 C.
Okay, at that speed, if you create, and you've got the ambient interstellar magnetic field, if you have simply a metallic strip across the sail, you will generate about a volt. And you can therefore use that as a power supply. And as you approach the solar system, the densities of everything, of not just particulates, but also magnetic fields, goes up. In particular, around almost all stars, there is a bow shock formation, the heliosphere. And in that formation, first there's a shock wave, there's compression of the magnetic fields, also compression of both neutrals and ion particles. And so if you can manage to steer it using J cross B, along the paraboloid, you get enhanced braking that's rather considerable, plus the power supply. So you should probably look into that.
We definitely should. I'd be very happy to find sort of in situ power and propulsion techniques.
Even
and
if,
lighten the load.
if just a few micro-Gauss interstellar field will give you, I think, enough power in the range of the wattage you may need.
Okay,
After all, it's CW.
thank you.
This will be the last comment or question.
Okay. John.
Some of us have been looking at the advent of high-temperature superconductivity. The wire is coming on strong now, and we can self-deploy this. The current expands the wire, and it can expand a membrane with it. And both of the talks, this applies because it pre-ionizes the interstellar hydrogen and helium coming through the membrane, and the field itself deflects these particles away. But in the process of doing that, it's reversing their momentum, and so it decelerates the probe. And all of this comes together very nicely for a variety of reasons, including what Jim Benford just mentioned about power generation, because in the same process, you're giving energy back to the supercurrent, and so it's a moving generator. And it's an exciting combination of technologies that I think are game changers.
Thank you. Thank you. Yeah, it's something definitely we should look into.